Video 2 for the Drivetrain design unit. Let's say we wish to build a pushing robot, so a robot designed to push things around. Well, we need a great force, but that's going to require two things. It's going to require high traction wheels and a significant amount of torque to drive those wheels. As we discussed in the first video, friction is a reaction force, so if there's no applied force, there will be no traction. So to maximize the traction, the torque applied to the wheels needs to be enough to reach the maximum static friction of the wheels. We want to take advantage of everything we've got. So that's why, if we think about cars, a car can have all the traction in the world, but if it has a small engine, it won't be able to push or pull anything. And this is why we don't see small cars towing big trailers. So we need to have a lot of torque, but we need to have a lot of friction between the wheels. So in our VEX system, there are a variety of things that we can use to help us gain traction. We have several different types of wheels, and each wheel has its own characteristic on different surfaces. So it's important for designers to experiment and to determine which wheel is best for their application. Now, friction between the wheels and the floor, it's not the only friction that's relevant. Friction can also act as a brake on the rotating components. In that case, you want to try to reduce friction, because any friction on moving parts within your robot reduces the amount of power getting to the output. And we have several parts designed to reduce friction. First off, metal against metal. You don't want that. So we use plastic parts such as the bearings, so the bearing, pillow block bearings, or the bearing flats. We also have those little black spacers. Now in our washers, you may have noticed that I have two types of washers, a metal washer and then a white washer. That white washer is actually made out of Teflon, and it's designed to reduce friction. So in certain cases you want friction. Between the wheels and the floor, you want friction. In other cases, let's say in your gear trains or in any kind of like conveyor belts, you want to reduce friction. Okay, now let's talk about some terminology. So first off, we have the drive wheel. This is what propels the robot. Not all the wheels on your robot need to be driving wheels. You don't have to put power to every single wheel. The next one is a turning point. This is the point around which the robot is turning. I'll go with rotates. This will come into play when we take a look at skid steers. The next important terminology is turning scrub. This is the friction caused by the wheels moving sideways. Another important terminology is a zero turn or zero radius turn. So this is a turn without moving forward. And then finally a chassis, and this is simply the structure that holds all of the drivetrain and the rest of the robotic components. Okay, so now that we've talked about the terminology, let's take a look at some different types of drivetrains. The first type is called the Ackerman, and you are the most familiar with Ackerman, believe it or not. This is a car-style steering system. So in this system, the back wheels are fixed, and then your turning wheels can turn. And basically, with this one, all of the wheels move in the same direction. And then turning is an arc. So what I mean by turning as an arc is the fact that the turning point is outside of the structure. Now there are some benefits to this. There is no scrub. So for an Ackerman style system, you don't have to worry about friction, which is, well, that's kind of true, kind of not true. There is a little bit of scrub in the back wheels as it makes a turn, unless you use a differential gearbox between the wheels, and that's something we talk about in robotics too. You know, what is a differential gearbox? An obvious drawback is no zero turn. And really what that means is that it's not as precise as it could be. Zero turn allows an object or a moving object to be very, very precise in how it puts its position. The next type, that's another really common type, is a skid steer. So in this one, the left and right sides have independent motion. So the left side can move forward while the right side is moving in reverse. Or they can move forwards at different speeds. Steering, then, is accomplished by varying the speeds of the left and right side. So we can have sweeping turns, in which case one side is moving faster than the other, or we can have zero turns, where one side is moving forward and the other side is moving in reverse. And you can also vary the speed for the right side moving forward and the left side moving in reverse to kind of change that zero turn as well. So some benefits. Obviously we get zero turn, which allows a robot to be very agile. And it does not require a dedicated steering motor. So what that means is that you're conserving your resources. You can now use that motor for something else. Now, there are some drawbacks. Scrub can be an issue. So as this is turning, between the surfaces, this wheel is going to try to, so if this is trying to make like a counterclockwise turn, friction is going to be acting this way against that wheel. That way. So there's going to be some friction because those wheels are going to try to slide across the floor. So that can introduce a lot of scrub. Now, a lot of times we can overlook this because for a zero turn, this is very good for precise positioning. Also, you'll find that this is the most popular design. Now, I know that what's most popular is not always right, but in this type of contest, usually what's most popular is because it works. Okay, the next type is a swerve drive. And basically, we have motors that are powering each wheel individually. And then each wheel could potentially be turned independently. And usually the way you see these set up is you got a motor on each wheel, and then on top of each wheel assembly you have some chain and sprockets, and then you have another motor on top that's dedicated to turning. So all the wheels turn through the same angle at the same time. These are really, really neat. I took some time to build one. What I found in operation, though, is that they're actually quite hard to operate. It takes a lot of driver skill to operate these. Also, they are resource intensive. If you've got 4 wheels, you have to use at least 5 motors in your drivetrain. So that can take a lot of resources. The next type is a crab drive, and really it looks very similar to the skid steer, but basically all crab drive is some sort of mechanism that allows the robot to move left or right quickly. So usually it uses 2 sets of skid steer, each pointing in different directions. Only one side is touching the ground at one time, but really it's just some sort of system that allows the robot to move left or right. That's really what a crab drive does. And what's nice about these is that you can keep the front of your robot pointing in the same direction at all times. The final system is an omnidirectional drivetrain. So this is one that can move in any direction at a given moment. There are a lot of similarities between this one and the crab drive. So for instance, looking at this particular design, we've got wheels on all 4 sides of the robot, and taking advantage of the fact that they're omnidirectionals means that we can move forward, left or right, do a very fast turn. There's a lot of benefits to that. Some other benefits: there's no scrub. And also, there's a lot of different configurations. I have several pictures on this page alone showing you how you could build one of these omnidirectional drives. Now, some downsides, though. You're going to, again, it's kind of resource intensive. You have to use a lot of motors. And another thing, some of these motors are going to be turned off part of the time. So you're using a lot of motors and you're not using them all at the same time. So doing a little bit of a cost-benefit analysis, it costs you a lot of resources and you're not using those resources 100% of the time. So it's something to think about. All right, that's going to conclude video 2.